Okay, so here we've got worked answers to the Chemsheets buffer solutions problems. Everything's already been done, it's just a case of running through it. As we work through, it's not just the correct final answer that we're looking for, you need to be showing working. A typical exam question, one of these would be an easier one, the ones we're starting off with here, 4 to 6 marks typically. And some of those marks are exclusively for proving that you did the right steps. You don't always just get all the marks for the correct answer. Now, listen carefully as I go through because I'll be pointing things out. Some of them are repeating themes. Buffer solutions have got a mixture of, the ones that we do calculations on at A level are acidic buffer solutions. They're mixtures of a weak acid and a conjugate base. And there's always more conjugate base than the little bit that comes off the dissociation. We've said that hundreds of times. In this first set of questions, question 1, it's just mixing. So you can see the correct final answer there. You might just be waiting for me to move on now. Just in case, work out the moles of acid, work out the moles of conjugate base, rearrange Ka as such. So you've got your acid to salt ratio, which is an important part of a buffer calculation. Now notice again, I've used moles here. Even though those are square brackets, because the units cancel, I could have divided them both by the new total volume. It would only have cancelled out anyway. It's perfectly acceptable to use mole over mole despite the square brackets. Anyway, you can see the numbers. I trust that that one was fine. I'm just going to give it 1 tick, but as I say, there are several steps in there that in an exam question would all be mark worthy. Part B is basically the same problem, but with different numbers. So I've got my moles of acid, my moles of conjugate base, which are present. Again, comparable amounts. You've got a 2.5 to 2 sort of ratio you can see there. Now look what I did. I've just written 10 to the minus pH, but I've shown the value of pH. Alternatively, solve that and write it in there. But you're rewriting the rearranged equation with numbers subbed in. If you prefer writing that in standard form, then good, do it. Show your value for concentration of H+, then negative base 10 log it to get your answer. Again, I hope that you've got all the same values there. If you worked out concentration and you've got the correct conc over conc there, which are these numbers of moles divided by the total volume, which is 45 cm cubed, so 0.05 dms cubed at the end, then that's also correct. Number 5, a slight twist on this question. We're told about a mass of a solid for the conjugate base. Now be careful here, you can see all the answers. The conjugate base is potassium ethanoate. Fair enough, only the ethanoate bit of that is relevant to the pH of the solution, but when we're weighing out these crystals, we have to account for the mass of the K+ ions which are in those crystals. So the MR to use is 98.1, not 98.1 minus the AR of K, okay? Because that's in the crystals contributing mass, even though it doesn't affect the pH. So that gives you those numbers of moles. As before, acid to salt ratio times Ka. Hopefully, through all the other steps you have to do, you get to 2dP, don't forget 4.77 as your pH. Question 2, again, if you need to pause at any point here to look at my numbers compared to yours, then obviously just do that. Question 2, we're part neutralising some of our weak acid. So look at the way I've laid it out. It's really, really clear. It has taken up a bit of space on the page, but so be it. Again, just for this first one, I'll make a few comments. So moles of methanoic acid. Methanoic acid's got a slightly funny formula, hasn't it? Because of it's just a single carbon, so it's a carboxylate group with just a H on it. So that's how much was at the start. Some of that gets neutralised as per the equation we've got in the box to form methanoate. It's all 1-to-1. It'll always be 1-to-1 if it's a question like one of these questions in an exam. So there's our moles of hydroxide added, which is the moles of methanoic acid used up, and also which is the moles of methanoate formed. So all in. Now don't forget, reactants used up, products formed. That's obviously the basics, but people do get it wrong. They get it the wrong way around all the time. So I've subtracted the moles of hydroxide from the moles of methanoic. So that's how much methanoic acid's left. And then the moles of hydroxide is the moles of methanoate that was formed, which is all of it that's present at that point. So you've got your moles of those substances present, you've correctly adjusted, you've added one and subtracted the other. We added the one to 0, which is why I haven't put that in. Then, yet again, acid to salt ratio, moles which are actually present. So you shouldn't be using 1.25 times 10 to the minus 2 anywhere in your getting H+ step, because that was the original amount of acid. Some of that has gone to form the A-. So anyway, there it is. You're going to see this in every question. Then I've rewritten it substituted. That's a very good habit to be in. shown my concentration of H+, then I've logged it, and I've even shown my expression that I'm using there, 4.35. Now, it's not necessarily 4 marks in an exam, it's probably more actually, but if you've done all those steps, then you're hitting all the marking points. I won't say as much about part B because it's, again, the sort of same thing again. We've had to adjust our numbers of moles present. So 0.04 moles of the weak acid were used up, leaving behind that amount there. And in the process forming the same number of moles of A- as hydroxide that was added. So those are my two values. Just be in this routine, just like I have been here. Substitute, unsubstituted, substituted, answer, and then use the answer, which will be a conc of H plus typically, to get the pH. If you've done all that, you will have the correct final answer, and provided your working's clear, you should be hitting all the marking points. Buffer calculations are usually not very well done in exams, so if you're ahead, excellent. Right, this time when we interpret the question, it sounds like there's a mixture of, there's a mixing method being used. So we've got a weak acid and to it is being added some methanoic. So that's like question 1 type problems then for us. So I've just gone through the ritual again, and hopefully you've done the same thing and got the same pH as me, 3.37. If you didn't, pause it, have a look, what went wrong, where was the mistake? And then some alkali is added to that buffer mixture. Okay, now some of my values that I'm using in question B are up here. So we had 0.024 moles of methanoic and 0.01 moles of methanoate at the beginning. Just bear in mind those values, they reappear down here. We've done this sort of problem before as well. Some of the hydroxide is using up some of the acid. It was already a buffer solution, but it's just changing. Okay, so rather than making a buffer solution from scratch, we've got one, and the thing here first of all is to identify that it's the methanoic acid component rather than the methanoate component. They're both present in this buffer mixture. It's the methanoic acid one, which being acidic is going to be neutralized by the hydroxide. So it's going to make even more methanoate, adding to what's already there. That's where you might have gone wrong with this. So we adjust our numbers of moles accordingly. There was some weak acid present already. Some of it's just been used up. Follow the numbers, hopefully they match yours, and we determine the number of moles of methanoic acid left behind. And then we basically add on the new moles of methanoic, this amount right here that's been formed by that reaction, to what was already present. There is now more A- present than there was a moment before. So that's why I've started with 0.01. I've added those two values together and I've got that. So we're not making a buffer solution to begin with. It already was one, and now there's even more A- and less HA. As before, so unsubstituted, substituted, answer. Can't really go wrong with that. And then that leaves you to a pH of 3.4. Depending on your rounding, you might have had a slightly different value there. I've got both values shown, depending on how you did your rounding. If you did answer over answer, no rounding until the very end, then you should get 3.99 times 10 to the minus 4 moles per dm cubed of H+. But if you actually tapped in those numbers to 3SF, and then you get 3.98. Either way, once you've done your pH, you've negative base 10 logged it and rounded it to 2dp, all answers should be 3.4. Question 4. Now I know that we always have problems with focus on this camera, but we can work with it. Right, question 4 then. Again, we've done this sort of problem before, so let's just go through it and check it. Hopefully all your values match. The moles of ethanoic acid that was there at the beginning, some of that was used up. Therefore there was less ethanoic acid at the end than there was at the beginning. Fine. Now this wasn't already a buffer solution as far as we can tell from the question, and so the amount of A-, in this case that's ethanoate left over, is just what was created by the neutralization. So that gives me these two values. Obviously you might have written them in standard form instead. Your acid to salt ratio is basically 17 to 8. But you wouldn't write 17 and 8 because it's 0.017 and 0.008, those are the actual numbers, times Ka. Now, all of the problems that we've done up to this point, and actually the next one too, we've been using mol over mol despite the square brackets. Obviously I mentioned that earlier too. Just be aware that you could in each one of those problems divided by total volume in dms cubed and shown a different value here to what I've been having as my HA over A- amount. I mean moles, it could have meant concentration. So if those values haven't been matching, they should be what I've written, divide by the total volume from the question. And obviously then just pay attention to what volumes were put together and what the total volume should be. It's a ratio ultimately though. 4.43 for that. Let's move on again. Now the plot thickens. Let's just take stock of where this story is going. They made a buffer solution in 4 part A by adding some alkali to the weak acid and then having a mixture of acid and salt, yeah, which makes it a buffer solution. Then what happens is this buffer solution is put to work. Some H+ is added. That would have made the pH drop massively, potentially, but being a buffer solution, it resists those small changes in pH. So the pH isn't going to change very much. It's only going to go from 4.43, the final answer is already on the screen there, to 4.4. So calculation steps to get to that correct final answer. The buffer solution contains weak acid and conjugate base. If H+ is added, it's the conjugate base in this mixture which will deal with it. So some A-, in this case again ethanoate, gets used up and a corresponding amount of ethanoic acid is formed. So our quantities of HA and A-, i.e. our acid to salt ratio, is going to change slightly. You can see what I've done there. I had to make sure that my number of moles of ethanoic acid increased by the correct value, which was the moles of H+ that was added. Again, everything's 1 to 1 to 1 here. And again, that same number of moles of H+ added, there's that much more ethanoic and there's that much less ethanoate present after it's changed. So these two calculation lines here are just me adjusting my numbers of moles from what there was before to what there will be after the H+ has been dealt with. And then again, I just plug it back into my acid to salt ratio, HA over A-. Again, those are in mole. And hopefully you get all the way to 4.40. If not, pause it, try and diagnose what went wrong. Was it that you subtracted and added the wrong way around? Pay attention. Right, question 5 is a good one. This could well be an exam question, so we're not limited to the sorts that we've just had. We're asked obviously about a buffer calculation, but from a different angle. They want the amount of A- that would be required for something. That's fine, we can manage this. So our Ka expression, we've rearranged it for that every time so far, acid to salt ratio, as we've been saying. There's no reason why we can't just rearrange it for A- instead. So that's all I've done there. Hopefully you can follow that rearrangement, multiply by HA, divide by H+, then you've got this. All we need is values that go into this expression. We've got Ka, we've got the concentration of HA, it's in the question. We just need to decide what the conc of H+ would be to satisfy the requirements of this question. We're told that the pH they're going for is 5.2. At that point, the conc of H+ would be 10 to the minus 5.2, because 10 to the minus pH is how we get conc of H+, which is this number of moles per dm cubed here. Now, this time we're going to end up using actual concentrations rather than moles in our acid to H+ this time around. So let's pay close attention to what numbers we're working with. When we do 10 to the minus pH, we get the concentration of H+, which is why I'm just reminding myself the units there are moles per dm cubed. Ka is given, it does have units, we're not too interested in the units, it's moles per dm cubed. We're told in the question that the concentration of the acid is 0.1 molar. Check the wording of the question if you need to. We must be consistent with our units here, otherwise we're going to be out by a factor of total volume, or 1 over total volume. So we're told that the acid is 0.1 molar. We've decided that the concentration of the H+ would be that value there. So if we do conc over conc, we are actually doing square brackets. Yeah, times Ka gives us that. That gives us our concentration of A-. I'm going to come back and make another comment about this if it was moles in a moment, in case you're looking at different numbers on your sheet. That isn't the correct final answer though. They're asking us for what mass of this substance we should use. So we're going to need a 2.82 mole per dm cubed concentration of A- to achieve that pH with this concentration of acid which has that Ka. So that's that many moles of methanoate. Methanoate is the A- in question here, so we'll be specific now. The total volume that we're told about, the solution volume, is 0.25 dms cubed, which means what we need for 2.82 moles per dm cubed solution is we need to put in 0.705 mole into this solution which has that volume. Thing is, we're dissolving this solid into that volume and we want that concentration. Now be careful here, we said this kind of thing earlier. When we're weighing out crystals of our conjugate base to dissolve in to make a buffer solution, there will be a counter ion, and it does it is present, and so it does contribute to the mass. So this being sodium ethanoate, the total MR is 68.0. Remember, our periodic table gives all ARs to 1 dp. So mole times MR gives mass. The correct answer, I'll accept this to just 3 sig fig, 47.9 grams required. That is that many moles, which in that volume would be that concentration, which would lead to all the criteria of the question being satisfied. Just quickly, to go back to a comment I made about if these were moles. You might have got that correct final answer, but you might be looking at different values here. If so, then well done, you navigated it correctly. This might have been where you went wrong. Now, the question tells you you've got a certain volume and a certain concentration of acid. Where is it? Question 5a, 250 cms cubed of 0.1 molar. So some of you may have gone down the line of working out the moles of methanoic acid, which is going to be 0.25 times 0.1, so 0.025 moles. If you do that, if you've got 0.025 moles there, then you're going to have to be dividing by a number of moles of H+. We get concentration out here. So if you didn't get your correct final answer and you did use 0.025, then what you should have done, assuming you got it wrong here, is you said, right, that's the concentration of H+, that's per dm cubed. You'd have to multiply that by 0.25. Because we haven't got a dm cubed, we've got a quarter of a dm cubed in the question. I won't actually work it out now, but 6.31 times 10 to the minus 6, divide by 4, or times 0.25 if you prefer. That value is what would have appeared there if you were going to get it correct, because then you'll have done mole over mole. So make sure that you're consistent with your units. We can get away with mole over mole, but if you have mole over conc or conc over mole, you're going to be out by a factor of, well, 4 here basically, or 0.25 depending on how you look at it, because that was the volume that you missed. Moving on again. Question 5b. I'm going to have to just quickly remind myself what 5b actually was about. I've got the answer in front of me, but 5b, oh yeah, it's basically another question on the same line. So I won't go on as much about this one. We're basically doing the same things again. We've rearranged our Ka expression for A minus. We've worked out what the conc of H plus would be from pH, 10 to the minus pH. Again, I'm using concentration of H plus there. Pay attention to the units. I purposefully left them on for students to see. Plug in your numbers in. You've got the concentration of the acid and so on. I got this conc of A minus needed. Now, it's only 25 cms cubed here. That's a relatively small volume. So we shouldn't be expecting to use kilograms of base to go into this stuff, of weak base. I work out that if that's how many moles per dm cubed it is, and we're only making 25 cms cubed, then that's the number of moles in a dm cubed. It gets scaled down a lot. There's the moles of ethanoate required for, again, achieving the criteria of this question, that pH, this concentration of acid, and so on. The counter-ion is Na+. So when we're weighing out crystals of ethanoate, it's actually sodium ethanoate. MR is 82. So we're going to need 11.3 milligrams. Probably more likely you'll have expressed it as grams of sodium ethanoate to achieve that number of moles in solution, which in this volume is that concentration, which when that's the Ka and that's the HA, and that basically gives you the pH that they're aiming for. Again, very well done if you manage that without any help, okay? But it is potentially an AQA exam question, a challenging one, but one that you could be asked exactly like that. Right, almost finished. So question 6, our default stance is that Kw is 1 times 10 to the minus 14, which through a calculation leads us to pH of water is 7. That's at 298 K. There's no clue that it will be anything else here, so we assume that. So the starting pH is 7. This is just an alkaline solution pH calculation problem. You should work out that the pH of the solution after some OH minus has been added is 11.29, and therefore answer the question fully, or else you haven't really got all the marks. The delta, the change in pH is that. Make sure you've answered that. The thing you might have missed is total volume. You had 100 cms cubed of water, to which 2 cms cubed of NaOH was added. So the total volume is now greater than 100. So that will have affected your answer. By comparison, then, there's quite a lot going on here. If we add that same amount of hydroxide but to a buffer solution, this is an acidic buffer solution. Again, the question is asking us for the change in pH, so there's almost like 2 questions here. First of all, the sort of thing we were doing in question 1, how much HA, how much A minus, what's the acid to salt ratio, therefore what's the conc of H plus, almost there, and therefore what's the pH. So again, if you need time to pause, have a look at the numbers, then do that. We're moving on. So you should get 4.58 as your starting pH. You need that if you're going to completely answer the question, which was about the change. Then again, we've done this sort of problem already. This time it was some alkali being added. That's going to use up some of the ethanolic acid in this buffer solution. The value that we had is going to get smaller. A corresponding amount of A minus here, ethanoate, is going to be formed, so its amount's going to go up. So for those two steps there, again, pause and take your time if you want to, if you need to. I've adjusted my moles of weak acid present. I've adjusted the moles of conjugate base present. I've correctly subtracted and added. I haven't gotten the wrong way around and increased the one that should have decreased. And those are my new numbers of moles present. Now, the bit in brackets, I've actually done it this time just so that I have at some point used total volume, okay, just so people can see it. If I put these values in, mol over mol, then we know that that's okay. Acid over salt times Ka. That's what I've done down here. We'll come back to the bracket in just a moment. There you go, look. Oh, actually, no, there's concentrations, aren't they? If I put that in, 0.0148 over 0.0102, mol over mol times Ka, I do get that same concentration of H+, which is what my pen's currently working on. pH it, negative base 10 log it, and you get 4.6. Good. But if you wanted to, you could take those numbers of moles, which you're going to need, and divide by total volume. The total volume is 102 cms cubed because 2 cms cubed were added to that 100, just like we mentioned earlier on. And you get concentrations, yeah, it's fine. Plug those numbers in. So either or, basically, moles or concs, and you get the same answer because it's the ratio, isn't it? Yeah, and they're in the same total volume of the solution. Either way, we're looking for the conc of H+, the pH, and again, to completely answer the question, if you paid attention well enough, the change in pH. It asks for it. So there it is. It didn't change very much. Adding those few drops of NaOH to water increased it by about 4 units of pH. Adding it to a buffer solution barely affected it. Now, I wouldn't expect that students have actually written as much as I have for this final question, which is to explain why the buffer resists the change in pH. You can pause this and read it at your own pace if need be. But I've just come up with a few ideas and I've gone as far as down the line of explanation as I could. So in water, there's nothing to sort of intercept, i.e. to react with that hydroxide. So it just remains in solution. The conc of OH- is much higher than it was before it was added, and pH goes up a lot. When we add it to a buffer solution, there's something in there that neutralizes it, which is the weak acid. The weak acid component of the buffer solution deals with the hydroxide, basically. If we were adding acid, it would have been the conjugate base which would have dealt with it. In the process of that, we're getting rid of part of our buffer solution, and the pH does increase a little bit. I know this is going slightly outside of the scope of the question now, but having added hydroxide, we've turned some of our weak acid into conjugate base. So now there's more conjugate base present. The conjugate base itself contributes to the pH of the solution because it's a weak base. It picks up H+ from H2O and releases hydroxide. But if a mole, it wasn't a mole in this question, it was a smaller value than that, but if a mole of hydroxide went in and we made a mole of A-, then a small fraction of that mole of A- is actually going to release hydroxide from the solution, and so a small fraction of the OH- added ends up being additionally present in the solution. Most of it is dealt with basically by the A- or by the HA in the formation of A-, which then doesn't ionize because it's weak. Now, I haven't read every single sentence on the sheet to you. You can always pause it and have a quick read if you want to. That's it for now. Well done if you followed me all the way to the end. You'll have gained the most from this. That's it. Thanks for watching.